Hi everyone. So let's get started. So today I want to discuss the principal component analysis, principal components analysis and a principal component regression. And we do the theory first, then do some lab session. And if we have more time, then we will do some practice. But I wonder if we don't have much time to do that. So first, I want to discuss the theory. So the principal component analysis and principal component regression is a way to reduce the dimension of predictor variables. So suppose we have many predictor variables, the 100 variables, 1000 variables. So typically this question arises when we process image or videos. So if we have even 24 by 24 image, that is very old, small size image for maybe characters. Then still the 24 by 24 is the 576. So 576 dimensional data set. For example, that this data is the grayscale data for each dot. Then we have the 576 dimensional vector, and each element that represents grayscale from maybe 0 to 15. So that's a high dimensional data. And we want to use these data to explain the response variable y. But since we have too many variables, we want to summarize this data into the smaller number of variables. Or even the economic analysis or some medical analysis, we have a high dimensional data, such as maybe gene data or a lot of individual level economic data. Then we want to summarize those into one variable. And generally, if we have p variables, that we consider the linear combination of those p variables. So maybe just an average or some weighted average, or even some coefficients may be negative. So the z sub m is equal to summation of j is equal to 1 to p, the phi sub jm, the xj. So linear combination. And often that we summarize the information into one or two variables, but generally we can think about z1 to zm, and m is larger or smaller to p. Usually much smaller than p. Then we can fit model the y on these zm's, so z sub 1 to z sub m. And this also reduces computational burden and avoid identification problem that when p is larger than n. Generally, the linear regression can fit this kind of model only if m is smaller than sample size n. But here, even if, sorry, I would say that usually we have n larger than p. But even if p is large, if we summarize the data into smaller number of variables, we can still fit this regression model. Yeah. And so this method to summarize the information of x1 to xp into the z1 to zm is called the principal component analysis. And this is the unsupervised learning, because, okay, we have y here, but basically these two steps are separated. So step 1 and step 2, and step 1 is just summarizing the data without using y. So this step 1 is called principal component analysis, and this is the unsupervised learning. Yeah. And today I want to discuss some more mathematical justification for this method. So PCA basically, we want to get most important information of x1 to xp as the z1, and how to extract z1. So the last time I explained in this way. So if we think about the direction of this, the n1 vector, n sub 1 vector, we can summarize this two-dimensional data most efficiently. So yeah, last time that we discussed that we minimize the distance between these points and this green line. But in general, that we have to think about the other way around. So we maximize the total variation when we project the purple dots onto this line. So if we think about the distance between these purple dots and this black line, the total variation, basically the average squared distance from these points to this straight line is the largest. So if we choose a different straight line, then which goes through the center, then always the total distance, the squared total distance gets smaller. So we choose this line in that way, and we choose the normal vector of this line as the principal component. So the coefficients of the principal component. So yeah, last time that we discussed several the properties, such as the first principal component, they usually have high correlation with all variables x1 to xp. So the mathematical formulation of this principal component is that so suppose the x1 tilde to xn tilde be row vectors of x. So x is a matrix. We have p variables and n observations. So we have the x11, so the first variable is, so maybe x21 up to xn1 and x12 up to x1p and to xnp. So each column means one variable, one predictor, and each line means the one observation. So for example, this one is the first observation. So we name this as x1 tilde. So this last one, so second one is x2 tilde, and the last one is xn tilde. So these are basically the points, so the purple dots in the previous scatter plot. So we project those points onto one plane, and if the distance between that plane goes through the center of the data, and if the distance between the plane, the average squared distance between plane and these points, x1 tilde to xn tilde, is maximized, then we say this direction u is the coefficients of first principal component. So that means basically we are thinking about diagonalization of the matrix. So we are searching for the unit vector u which maximize the norm of x tilde u. So basically we are searching for an eigenvector with largest absolute eigenvalue. So so we normalize this. So suppose the Euclidean norm of the vector w is 1, so the w is a unit vector, then basically we maximize this quantity. So that means that we are looking for eigenvector of the largest eigenvalue of the x transposed times x. Yeah, so basically we diagonalize the matrix, then we can find the principal components of this matrix X. Yeah, and the second principal component corresponds to the eigenvector for the second largest absolute eigenvector of X prime of X. Yeah. And before doing the principal component analysis, usually we do the standardization. So that we make each column vector has mean 0 and variance 1. And mean 0 is just for simplicity. So if everything has mean 0, that we can ignore the intercept. And so we don't really have to worry about the plane that to be projected goes through the center of the data. So always the center of the data is the origin. And the variance is for standardization. So if columns have different variance, then basically principal component decides that that variable is more important than others because we maximize variance. But in such a way, the method is not scale free. So if the variable is reported as centimeter, then that means the variable is 100 times more important than the same variable in meter. So that isn't really consistent. So usually we standardize all column vectors of X into mean 0 and variance 1 vector. Yeah, so if the standardization is not done, principal components will be similar to a column vector with largest variance. And the principal component is not scale invariant. So usually we do this standardization. In statistical packages, usually you have options to choose either that variable is scale free or that variable is standardized or not standardized. So this is the way to do principal component regression. And actually, sometimes I feel that I don't really understand the principal component analysis, principal component analysis and principal component regression, because usually we want to have a smaller number of variables for simplicity, but this principal component analysis takes significant amount of time, and you can find that if you have maybe more than 500 or maybe more than 1,000 variables, then principal component analysis takes too much time. So that means if we have very high dimensional data, such as maybe the 10,000 dimensional data, then you cannot really summarize the data by principal component analysis. It takes too much time. So usually the time required to diagonalize the matrix is order of p cube. So if p gets larger, then the time required is proportional to p cube. So that means, p is 10 times larger. It takes 1,000 times the more time to diagonalize the matrix to get principal components. So I'm not sure practically how to deal with it. And I think that we have some approximate algorithm for principal component, which is much faster than full principal component analysis. So, but I don't really know the details. So I think if you are interested in that, you can do research on that theme. Maybe there's some other mathematicians or computer scientists know more about it. Yeah, I think that when we use R, usually 500 dimensional data, that's fine. And larger than that, we have trouble to get principal components. But some packages have some randomization algorithm to do principal component analysis. So maybe that's the way to go. So logically, it's not 100% clear how PCA save time for analysis. Do you have any questions so far? So next is the principal component regression. So step 2. So we summarize the data in step 1. So we do the regression in step 2. And this is just a linear regression. So we regress y on z1 to zm. So it often performs better than the multiple linear regression since information is efficiently summarized. Right. So because suppose we have the 50 important variables, but if we summarize those 50 variables into 2 variables, maybe it includes most of the information of 50 variables. So in such a case, we only have to introduce 2 variables. So then it's much efficient. So it often performs better than multiple linear regression. Probably the AIC is not a fair method if we summarize the data into smaller number of variables. Of course, the AIC penalizes the number of parameters. So if we have smaller number of parameters, then of course the AIC is smaller, so better. But in reality, if we do more objective criterion, such as the cross-validation, the PCR often performs better than just usual linear regression. And it can be combined with lasso or stepwise forward selection. That is, the principal components are used in lasso and or stepwise regression. So yeah, so suppose we think about forward regression. Maybe if we have 50 important variables, forward stepwise regression choose 50 predictors, but if the information has been summarized, usually we don't need that much information. Yeah, that is especially true for image analysis, where the dimension P is very large. And it avoids the parameter identification problem when P is larger than N. Yeah. Yeah, so linear regression only works when P is smaller than N. So, but the principal component regression, originally we may have 1 million variables, only 1,000 observations, but still we can summarize data into maybe 100 principal components, then we can do regression. And here, the test MSE of principal component regression by the number of components. Yeah, so test MSE is purple, and yeah. Sorry. Sorry, I'm not sure what's the difference between these two graphs, maybe for different data. Yeah, so basically the purple line is the test MSE. So even we do principal component analysis. I see. Just a moment, please. Sorry. This is from PCR. This is from usual linear regression. So the PCR, we have maybe around here, 10 to maybe 20, 23, or so maybe 15 to 23 variables is optimal to minimize the test error. But if we use usual linear regression, the optimal point is probably around here, maybe 32 or 33. So since principal component regression summarize the data first, so that we can make the model more, smaller. And also the mean square error, the level of mean square error is about 40 here, but here almost 40. So probably marginally, maybe slightly larger than 40, maybe 45 or something. So with smaller number of variables, that we can get basically a slightly better model. And this is especially true if original P is large. Yeah, so this is the principal component regression. So next slide is a different topic. So do you have any questions, comments? So even if original data set is very large, we have very large P, the usually principal component regression only takes a few variables, such as maybe 15 or 20. Yeah, when I was a graduate student, I see some examples. We have several pictures of coffee cup. Maybe background is just the picture of the room or something, and the coffee cup here. And the next one, maybe coffee cup looks like this. And just we want to calculate the angle of the coffee cup, and all other informations are redundant. Maybe the picture of the desk, maybe the table, or a picture of the chair, and the maybe background. We have some plants or something like that. But we want to ignore all of those information, and we just calculate the angle of this coffee cup. Then do principal component regression, and we only needs maybe only a few variables, like 20 variables. Yep. And the next section is the partial least squares. So this is similar to principal component regression, but it's different because when we summarize the data of x1 to xp, we use the information of y. So depending on y, the way to summarize the data are different, right? So yeah, so I think it's not easy to come up with a good example, but suppose we have many kind of variables that, like the temperature or GDP growth, or maybe consumer satisfaction, or maybe acceptance rate of Wayne State University. But suppose that we want to predict the just consumer price index, then probably the temperature in Detroit doesn't matter much for that consumer price. But maybe unemployment rate or GDP growth, or possibly college's acceptance rate is important to predict business cycle and then consumer price. So even if we have many variables, maybe the quarterly average temperature of the maybe 1,000 US cities, those variables are basically garbage to predict the CPI. So in such a case, when we summarize the data, we want to ignore those data, and we want to summarize just important data. So it makes some sense that to use the information of y to summarize the variable x1 to xp. So the principal list, the partial least squares, they use that idea. So idea is very similar to principal component, but we have basically mixed the step 1 and the step 2. When we summarize the x1 to xp, that we use the information of y. So that is a kind of cheat, right? So we summarize the data first, then use summarized data to predict y. That is the legitimate prediction. But when we use the information of y to summarize data, that's a kind of cheat. But still, sometimes it works better than principal component regression. in terms of cross-validated error. Yeah, so yeah,
so
yeah.
Is this one also unsupervised, or is this supervised?
This is the supervised learning. So yeah, supervised learning.
Okay.
Yeah, so the principal component regression, we have the first step PCA and the second step the linear regression. So this part is unsupervised. And this part is supervised. But the principal, partial least square method, this is the just combine these two methods. So overall, this is supervised, since we are using the information of Y. Yeah. And generally, we may have multiple response variables. We don't deal with those models, but it's possible to consider multiple variables as response. But here, we only think about the case that we have just one response variable, as usual, and we want to summarize information of x1 to xp. And algorithm that uses linear regression. So we fit the z1 on all predictors x1 to xp. So we do linear regression. Then we have estimated coefficients, right? So we use those estimated coefficients as coefficients of components. So like similar to principal components that we use these coefficients to define Z1. Then after that, what will we do? So, okay, so yeah, so now we have determined Z1. So we want to determine Z2. Then we regress each of xj on Z1. So we have residual, the Rj. So basically, this is the additional information in x sub j beyond Z1. And we use this Rj, and we regress Y on these Rj's, R1 to Rp. Then we get some coefficients in linear regression. And we use these coefficients as coefficients of Rj. Then Z2 is the component. Okay, so remember that the Rj is a linear combination of x1 to xj, right? So because the z1 is the linear combination, so this is the linear combination. Linear combination of x1 to xp. So that means the Rj is xj minus linear combination of x1 to xp. So Rj is also linear combination of x1 to xp. So that means the linear combination of Rj, so this entire quantity is also linear combination of x1 to xp. So still the z2 is a linear combination of x1 to xp. So we define this as z2. So the algorithm is different from principal component analysis. And in this way, we can optimize z1, z2, z3, and so on to predict y. Yeah, and once you get z1 to zm, that we can do multiple linear regression, y on z1 to zm. And we evaluate optimal m by cross-validation. Do you have questions on the idea of the partial least square? So it looks ad hoc. So when we summarize data, we use the information of Y. So it's not really a fair method. But anyway, in this way that we can summarize data efficiently. So finally, the model can be better than the principal component regression. Yeah, here the dotted green line is the PCR, the direction of PCR. So it summarizes the information of this X1 and X2 the most efficiently. So we deduct the most important information in X1 and X2. And the solid line is the line by PLS, the partial least square. So even though this has lost some information for X1 to X2, but it's optimized to predict the response variable Y. I think response Y is maybe sales, maybe. So maybe sales depends more on population rather than ad spending. So in such a case, maybe this slope is a little smaller than the dotted line. Yeah, so basically this is the end of the PLS. And now that we discuss some the properties. So N is sample size and P is the number of predictors. And the traditional statistical models deal with the case with N is much larger than P. So typically, for example, estimate blood pressure BP by age, gender, and BMI, body mass index, with sample of 1,000 people. So N is 1,000, P is 3. So the algorithm, okay, so P is fixed small number. And typically the time order is order of N. So P doesn't really matter and N is large. So the time order to calculate, for example, regression line is the order of N. So if N is doubled, just the time is doubled, that isn't really a big problem. And parameters have some asymptotic properties. So if we have very large N, we can get arbitrarily accurate estimates for parameters such as beta, the slope. And high dimensional data. High dimensional data means the P is much larger than N. And in such a case, actually some models are not estimable. So one example, some models are not estimable, such as linear model. And the example is this. So for example, we have the 20 people and each people have DNA information, and the DNA information have each person has the 500,000 DNA mutations. So we have the 500,000 variables, even though we have sample size 200. Yeah, so in such a case that we need some assumptions to estimate parameters because we have so many variables. So if each variable have one parameter, one coefficient, then we need some assumption. So parameters cannot be identified correctly. We need some assumptions, such as we penalize the size of P so that only a few of them becomes non-zero or something like that. And more importantly, computationally, usually the model requires the much higher order of time. So if P gets larger, the time needed to estimate the model is often order of P cube or even larger. For linear regression, if we have P variables, then the time order to estimate the model is order of P cube. So if we have twice more variables, then we have 8 times more time. We need 8 times more time to estimate the model. So that's a huge challenge to deal with a big data. So when we say big data, just our image is, okay, so rather than 100 people's data, we have the 1 million people's data. But that's not a problem in statistics. If we have 100 to 1 million, then we have 10,000 times the more data. So it takes 10,000 times the more time. But that isn't really a problem. But if the number of variable is 10,000 times larger, then computational time is much larger, 1 trillion times larger. So we have to have much more efficient algorithm. So that is a huge challenge for high dimensional data analysis. So when we say big data analysis, the usual people think that just the data size is large, but the statisticians think that as we have a large P, so we have more fundamental problems. Sometimes models are not estimable. We cannot get reliable estimate of parameters, and the computational time is very large. I would not say exponentially, but it's much larger. Yeah, so linear regression takes the order of the P cube, but also I discussed that the principal component analysis takes the time order of P cube. So basically we need the inverse matrix of P by P matrix. So yeah, we need almost the same time. So why PCA, principal component analysis, is time efficient? So it really depends on the modified algorithm, I believe. So if we fully calculate the principal component principal components of matrix, then it takes time order of P cube. So probably we have much more efficient algorithm, for example, to calculate first few principal components. Yeah, so this is just a conceptual figure to explain what happens when P is larger than N. For example, if we have 20 observations in the left figure, then we can estimate the straight line by least square. And the 2 observations, we have no errors. We can still estimate the straight line. If we only have 1 observation, can we estimate the straight line in any method?
No.
In usual, ordinary least square, no, right? Because we have this line and this line not estimable. But the Bayesian regression, for example, the rich regression, we can estimate. Right? So rich regression, basically we minimize basically slope square, right? So if we don't penalize the intercept, then basically the rich regression is this. So slope is 0. So we have no penalty on slope. Then still it goes through the data. So we have no errors. So that is the rich regression. Right? So it's possible if we use the regularization method, or we use the Bayesian methods. Yeah, sometimes I ask a question to estimate the straight line with 1 observation, like in PhD prelim. So a fewer number of observations, usual model is not estimable, but if we do other methods, sometimes we can. And what goes wrong in high dimensions? High dimensional data are very counterintuitive, and we have several problems. And for high dimensional data, so the cross-validation is strongly recommended to choose the model because AIC, or the equivalently Marlow's CP or even BIC, are unstable. And usually it chooses the model which is too large. And mathematically, it depends on the unreliable estimate of sigma square. Yeah, but at least practically, it does not work well. So AIC information criterion needs the correct sigma square, but the sigma square may be underestimated if we have too many variables. Yeah, and the training error, adjusted R square, and other traditional statistics for training set do not work. It always selects a larger model, which makes zero training error. So just use CV for larger model. So here is an extreme example. So fitting a regression model with 20 observations and predictors x1 to x20, but these are just random numbers, so that the truth is they are totally uncorrelated to y. Then this is the model and the model performance in terms of, I think this is R square. Yeah, R square, yeah, R square. And this is training MSE, and this is test MSE. If we choose more observations, then R square goes to 1. 20 observations for 20 variables for 20 observations. We can explain everything perfectly. So R square gets to 1. And training error gets smaller. If 20 observations for 20 variables for 20 observations, we can explain everything. So error is 0. But the test error gets just larger and larger if the number of variable gets larger, because we fit y is equal to beta naught beta 1x1 plus maybe beta pxp plus epsilon. But x1 to xp are just random numbers. So that means it adds just noise to predict y. So test error gets larger. So larger R square or a smaller training MSE mean nothing. And we have to focus on test MSE or cross-validated MSE. And the next one, this is a simulation to see what will happen when we have too many candidates of predictors. So suppose that we have 20 true predictors to explain response y. This is simulation. So we know that 20 predictors are truly related to y. But we have the 20, 50, or 2,000 candidate variables of predictors. So in the first scenario, all predictors are truly related to y. But in the second scenario, we have only 20 correct predictors and 30, irrelevant variables. And the third one, we have 20 true predictors and 1,980 irrelevant variables. And what happens when we use these data set to fit the response y? And we use the lasso method here. So basically this section is a little more general argument. So we just go away from the PCR or PLS, and we use the lasso regression. And here is the result. So P is equal to 20, P is equal to 50, and P is equal to 2,000. And we optimize the number of predictors based on the cross-validation. And if P is 20, certainly, if we choose all variables, the error is smallest. So test error is smallest at maybe 1.2 here. So 21 variables are chosen. If P is equal to 50, the cross-validation chooses, yeah, I think the cross-validation or maybe the validation approach. Anyway, so the cross-validation or similar method that chooses the 28 variables. So that means we have 50 variables, probably 20 variables, the true predictors are selected, but the some variables are just as good as true predictors by chance. So we have many candidates of predictors. So some are truly related to y, but the some are by chance related to y. So if you want to develop a prediction model, you cannot really distinguish those. So the best way is to include both variables. So we include the 28 variables. So it's more than the, sorry, this is degrees of freedom. So I would say that the 20 variables here and the 27 variables here. So we exclude intercept. Excluding intercept, we have 27 variables. If we have 2,000 candidates of variables, then we have 69 predictors chosen. So we have probably, hopefully, the 20 true variables and plus 49 variables, which by chance are highly related to response. Possibly, maybe in the worst case scenario, we missed several ones, missed the true predictors. Then we choose, fake variables, which are just by chance correlated to the true response variable. So if the P is large, it's really hard to choose the best model. So even use the cross validation, we choose at least the 49 redundant variables. And possibly we miss some true predictors and we choose some fake variables. Yeah, so the lasso selected the more variables than the true set of predictors, and this is called the curse of dimensionality. So yeah, so lasso, you often drop the many variables if coefficient is small enough, but actually still we suffer from these redundant predictors. Yeah, so when true predictors are hidden in a forest of predictors, it's hard to identify all of them. The lasso chooses the more variables to make sure that the all important information is included in the model. So usually the including additional predictors don't hurt much. So it adds some noise, but it's better than missing the important information. And for this is another, do you have any comments, questions for now so far? What time? Still 6:20. Okay. So for high dimensional data, even with an appropriate variable selection procedure such as cross validation, at first the multi-collinearity is severe. So that may be important for your final project. So in linear regression with fewer candidates of predictors, okay, the final model includes 3 predictors, and house price is explained by square footage, year built, and the number of bathrooms, and everything is interpretable. More bathroom, the house is more expensive. The larger house, more expensive. Newer house, more expensive. 1 year newer, the value is maybe $1,000 more, and so on. But this kind of very large data analysis, we have 20,000 candidates of variables. Usually multi-collinearity is severe, and we cannot see the many significant variables. I think that even that problem can happen in smaller data set, like 50-30 project. Once the one student brought me the final project data set, and he said that he used the stepwise regression, and the maybe 7 or 8 variables were chosen, but the no variable is significant, statistically significant, and it sounds problematic. And I just see the data and his result, and I dropped several variables, and I just keep 2 or 3 variables, and everything becomes so significant, very highly significant. So, and he was surprised, but that can happen. So probably the prediction model itself is very reasonable, but since we have so many predictors, it looks all insignificant. So in some sense, the 58-20 final projects, you have less interpretation than 50-30 projects, because the data is large and the more automatic computational methods. So it's harder to interpret coefficients. And the selected set of predictors may not be a unique best set. For example, two totally different sets may be as good for prediction. Yeah. For example, the x1 and x2 are almost the same variable in different definition. So suppose y is the GDP growth and x1 is the CPI, consumer price index, and x2 is the price index for personal consumption expenditure. So these two are almost the same. But the yeah, so similar variables. So maybe we need just one of those. So that's possible case. Maybe the to predict GDP, the important thing is consumer price and maybe industrial production. And the third one is, I don't know, some unemployment rate. And the fourth one is maybe the overall, maybe the weather or something like that. Then X13 is weather in New York, and the X15 is weather in Boston. And anyway, so these are similar variable. But just we only need the one variable to explain the overall weather in that season. Or unemployment rate, X10, and X11 is maybe unemployment rate for maybe some 20s or something like that. And just we need one variable to explain the labor market condition. Then just one variable is enough. So in such a case, it's possible that the two totally different sets have almost the same information and so almost the same performance to explain why. So the variable selection itself may not be meaningful also. So that's possible case. Yeah, so generally high dimensional data analysis is more computational and like the engineering method, and the less, theory, less interpretation behind it. Even the model is good. Sometimes that cannot be used. Once I heard from a banker, he developed a good, model to estimate the default risk of customers by neural network, but he cannot interpret the model. So executives don't, adapt the model because, it's too risky if that's a black box. So that's always a problem in high dimensional data analysis. So on the other hand, we have more potential, right? So statistical analysis between just the two variables between y and x. If we see a scatter plot, a time, plot, then we can see almost all information. Yeah, one professor said the 90% of your statistical analysis is done if you make plots and summarize the data. But the high dimensional data analysis have more, opportunities. The very complicated data set, with very complicated data set, you can do some non-trivial task. For example, based on the videos that you can make an algorithm for, autonomous driving. So there are so many variables and people cannot interpret it, but finally you may find an algorithm to drive car automatically. So that cannot be done with interpretable model. So even if black box, that can be very useful. Probably that is a source of innovation in the future. Do you have any questions? Yeah, so if you are thinking about getting a job with statistics, one way is to interpret something like economists. So whether some variable, for example, typically unemployment rate affects the price level, inflation. So that isn't really clear, right? So, and they are really, serious to see whether that really affects the, inflation. That is one way to go, or medical applications. So this, chemical really affects the patients positively or something like that. And another way to go is with very complicated data that you may find something that which is not intuitive. So that is another source of innovation. Okay, so next one. Do you have any questions? Yeah, so this is the lab session for PCR and the PLS. And we use this PLS package for both analysis. And we use the HITRS data. I think this is the same data set from the previous lab session. So HITRS data is here. So 263 players, the data, baseball players data. And basically, we want to explain salary by other variables. And that first, NA omit. So this omits the lines with at least one NA. So that is a pretty convenient function. And that we set X as the model matrix, just the predictor matrix X, excluding intercept. And Y is the response variable salary. Yeah, then principal component regression can be done by the PCR function, the salary on predictors. And we specify the data set. And we have several options. The one is scale. So remember that usually we make all variable standardized. So have mean 0, standard deviation 1, or variance 1. So scale is equal to true means that we standardize the data. So standard deviation of the variable is set to 1. So default is false, though it does not transform in our algorithm. So here the scale is true, so we scale variable. So these variables have different units, so it's reasonable to scale variables. If all variables are in the same unit and the size itself has some meaning, then possibly we don't want to scale it. And the center is equal to T. This makes all predictors has mean 0. So default is true. So it doesn't hurt if we just shift the variable to make center equal to 0. So in this case, we specify scale is equal to true and the center is equal to true by default. So both are true. Then validation. So principal component regression, we have to choose the number of components, the best number of components. So this function has functionality to optimize the number of variables M. And here is the result. And this is the mean square error, cross-validated. I'm not sure what is K. Oh, actually tenfold cross-validation is the default. And you can see that the 0, maybe 1, 2, 3, 4, 5. So as long as you have just one component, probably it's sufficient. Possibly maybe 5 is better than 1. And more than that, basically it hurts. So the 5 is maybe the best components, maybe 6 or 7, I'm not sure. So that is the result. So if we summarize by principal component analysis, maybe the one variable explains almost everything. Maybe slightly more information if we add 4 or 5 more variables. And this is the summary of this model. And you can see the CV and adjusted CV. So CV is usual cross-validated error. Adjusted means it adjusts the sample size. The cross-validation only takes 90% of the data to fit the model. So we adjust it, and so that the true expected the size of error is a little smaller. right? Because if we use the 100% of observations, we have slightly more accurate estimation. And you can see that the CV is minimized at actually 7. So I thought it's 5, but the 7 slightly smaller. So 7 components, the CV is smallest. Adjusted one, the size is slightly different, but still the 7 is the best. So CV is just a good enough method. So maybe you can just focus on CV. Both are almost equivalent. And the training, yeah, so we choose the 7. And also it reports how much percentage of variance is explained by the first few components. And actually the first principal component explains the 38.3% of variability in X. So we have how many variables? I think the 19 variables, but the first component explains 38%. And the first and the second component, if we use 2 components, that explains 60% of variability in X1 to XB, X1 to X19. And 3 components, 71%, 4 components, 79, 5, 84%, 6, 89, 7, 92, 8, 95, and so on. So our best model is 7 components. So 7 components, first 7 principal components have 92% of variability in X. And here, 46.69, this means the 7 components explain the 46.69% of variability in salary. So salary have some variance, right? So variance of salary, suppose this is 100, then if we use 7 components, then salary on these 7 components, beta 7, Z7, and plus epsilon, then variance of epsilon is equal to basically 53.31. So 46.69% are explained by these, and the remaining 53% is in error. And this is, but actually the in sample, the training error size. So actually, the training percentage of training, so the percentage of salary explained in the training set. So it gets larger and larger if we add more components. Sorry, here. So if we all 19 variables, the 54.6% is explained, but actually that is a kind of overfitting. So the best model is 7 components. So we expect maybe the 46%, 47% is the training error. So in the test set, probably it gets slightly worse, like 55% or something. But if we use all components, it gets even worse, such as like 40% or something. Any questions? And the next one is the partial least squares. So basically we do similar thing, but we use the information of Y to summarize the data. And we use the PLSR, partial least square regression function. And the options are almost the same. So just it works in the same way. And the partial least square, actually around here, maybe 11 is the best. 11 or 12 is the best number of components. And by cross validation, you can see that 344.7 is the smallest. This is also close. So 11 components, we minimize the cross-validation. And actually the cross-validated error is slightly smaller than previous one. Previous one, I think the 354? 346.1. So almost the same, but the 1.4 smaller. Here. So yeah, so 11 components are chosen. So we cannot say which model have larger number of predictors. So we have different ways to summarize data. So sometimes maybe PLS choose smaller number of variables, sometimes larger number of variables than PCR. And here 11, so 97% of variability in X is summarized here. So last time that we chose 7, so maybe it's good to compare at 7. So last time that about the 92.2% of X is explained by first 7 components, but by PLS only 88%. It's smaller. But this number 52.34%, this is larger than before. So PCR, the 47% of variability in salary was explained by the first 7 components. Here, 52%. So this percentage, 88 is smaller than the PCR, but the 52 is larger than the PCR. So it's optimized to explain salary. And 11 components is the best by cross-validation. Yeah, and a sample code for validation set approach can be found in the textbook. So this uses cross-validation. Yeah, possibly, for example, time series analysis. If we have data from 1970 to 2020, the time series have some time structure, so we cannot divide data randomly into several pieces. So maybe we can just use the 1970 to maybe 2005 as the training set and the remaining one as test set. So some data we cannot simply do cross-validation, so validation approach may be useful. Yeah, so that's the principal component regression and the partial least squares. Do you have any questions? Yeah, I think that we don't have time to cover exercise. Exercise 8 is available on the website. So if you're interested in, then you can do it for your hands-on experience. Okay, so if you don't have a question, that's it for today. I haven't graded the midterm, but I will do within a few days. Oh, and the next week on Tuesday, next time on Thursday, I'm thinking to schedule your final presentations. So yeah, just attend the lecture. Or if not, I will send an email beforehand. So just respond to it for your schedule. Yep. So that's it, and see you on Thursday.
Thank you. Have a good night. Bye.